Welcome back. In this module, we're going to learn about how to solve related rates problems. Let's motivate the topic of related rates with a real-world problem. Suppose there was a heavy storm that caused the roof to leak in Kathy's kitchen, creating a rapidly expanding puddle of water on her kitchen floor. Moreover, imagine that the area of this puddle is growing at a rate of 16 centimeters squared per second. Then the question is, how fast is the radius of the puddle growing at the precise instant when the radius is 10 centimeters? This is an example of a related rates problem where we're given the rate of change of certain quantities, here that's the area of the puddle, and are required to find the rate of change of related quantities, here that's the radius. So how do we solve problems on related rates? The procedure can be broken down into 4 discrete steps. The first step is to identify the changing quantities, possibly with the aid of a diagram or sketch. For our puddle problem, there are 2 quantities that are changing with respect to time t. These 2 quantities are the area of the puddle, along with its radius. Let us denote these 2 variables, a and r, respectively. The second step is to write down an equation that relates these 2 variables. Here, a and r are related through the well-known formula for the area of a circle, a equals pi r squared. The third step is to implicitly differentiate both sides of the equation with respect to t. Here, this gives dA dt equals 2 pi r times dr dt. Looking at the result, observe that we've now obtained an equation that relates 2 rates of change, dA dt and dr dt. This leads to the fourth and final step. We substitute into the equation the known rates of change, along with any known quantities, and solve for the wanted rate of change. Since the puddle is growing at a rate of 16 centimeters squared per second, dA dt is therefore 16. Moreover, the question, how fast is the radius growing, at the instant when it equals 10 centimeters, translates to the mathematical problem of finding dr dt when r is equal to 10. Substituting all of this information into the equation, we get the following. Rearranging for dr dt, we therefore obtain 4 on 5 pi. That is, the radius of the puddle is growing at a rate of 4 on 5 pi centimeters per second. Let's study another example. Suppose we have an open hemispherical tank that's filled to the brim with water. As the water evaporates in the sun, its volume goes down. Now suppose when the water depth is h meters, the volume of water in the tank is given by the following equation. The question is, assuming the height is dropping at a constant rate of 10 centimeters per hour, how quickly will the volume be decreasing when the height is precisely at 2 meters? Using our 4-step framework, we first identify the changing variables with respect to time, which are volume and height. Let us denote these v and h respectively. We then link these variables through an equation. For this example, such an equation was directly given to us in the question itself. We then utilize implicit differentiation to obtain the following. The final step is to plug in all our available information, and then solve the wanted rate of change. Since the height is dropping at a constant rate of 10 centimeters per hour, we therefore have that dHdt equals negative 0.1. Moreover, the question, how quickly is the volume decreasing when the height is 2 meters, translates to the mathematical problem of finding dV dt when h is equal to 2. Substituting all of this information into the equation gives dV dt to be negative 1.2 pi. Therefore, the volume is decreasing at a rate of 1.2 pi meters cubed per hour. Alright, it's time to pause the module and have a crack at the following two practice questions. And here are the short answers to the practice questions. We followed the four-step framework of first identifying our changing variables before linking them through an equation. We then differentiate both sides of the equation with respect to time, followed by substituting in our given information, and then solving for our wanted rate of change.